Hi, and welcome back to Chem with Chem. In this session, we're going to be working question 5 of Chemistry Paper 2 from the January 2022 sitting. If you've missed questions 1 to 4, then be sure to check them out on the channel. Please also check out the other content materials that are available. I hope you'll find them useful. And consider subscribing and turning on post notifications so you can be alerted the moment when new material is added. Enjoy. Let's get right into it. So this is organic chemistry, reactions of organic compounds. And it's all about the patterns. Organic chemistry is really meant to be therapeutic. It's a break from all those calculations, 6.02 times 10 to the 23, and so on and so forth. So it's meant for you to just relax and just flow through it. All right, part A. The fully displayed structure of compound C4H10, that's the molecular formula. Now, the fully displayed structure of this compound is shown in figure 4. Right? This is compound B, and we should just carefully look at anything that jumps out at you. First thing that jumps out at me here is the fact that there's a carbon-carbon double bond, which is telling me, hey, alkene. It's telling me that it belongs to the family of organic compounds called the alkenes. All right. Number 1, and before we read the question, there we go, we have answers already. Deduce the homologous series to which compound B belongs. So the carbon-carbon double bond tells us that it belongs to the alkene series. It is unsaturated, so we're going to say alkenes. And just like that, we're off to 1 mark. And they ask us to write the name of compound B. All right, so the name is going to be determined by the number of carbon atoms that are present and the functional group that's present, which is what gives it its last name. And also, in this case, the position of the functional group. So we always count from the side wherever the functional group is, that carbon will get the smallest number. So this would be 1, carbon 2, carbon 3, carbon 4. But we have 4 carbons, and there's a prefix for when we have 4 carbons. All right, when we have 4 carbons, the prefix that we use is called but, B-U-T, not but, but. So we'll have but, and then we'll have the ending part of the name. We said that the ending part is what tells us the family that it belongs to. So this would be butene. All right, let's get the color right. So this would be butene. Now, because that functional group could be in the middle here, we can just say this is normal butene. And we normally put N-butene there. We could also call it but-1-ene. All right, and we'll look at why we call it but-1-ene based on the question that is coming. All right, compound B exhibits structural isomerism. Part 3, define the term structural isomerism. So it's the existence of organic compounds with the same molecular formula but different arrangement of the atoms in space. Or we could say organic compounds having the same molecular formula but different structural formula, because structural formula pretty much shows you how the atoms are connected to each other in space. All right, so we'll say right, and they want us to draw the fully displayed structure of any structural isomer of compound B and name it. So let us just draw back what compound B is so we can have it as reference. So we're given this compound B is what we have here on the side. And of course, we have to remember that all carbon atoms must be taking part in 4 bonds because carbon is tetravalent. Tetra means 4, valent means it has 4 valence electrons that can take part in bonding. So all carbon atoms must be taking part in 4 bonds. Now we can have, there are 2 other isomers, 2 other structural isomers of this compound. Butene or N-butene, but-1-ene. There are two others. We could have one where we actually move the carbon-carbon double bond from the end to the middle, right? So we're going to draw what that would look like for one of the answers. We're going to just represent both of them, and you can do whichever one you're comfortable with, as long as you get the concept. So this would end up looking like if the carbon-carbon double bond were to be in the middle, then this is what the compound would look like. And they also ask us to name it, so we'll go right ahead. So the carbon-carbon double bond is now in the middle, so we have to take care to ensure that each carbon atom is still participating in. So there we go. Still have the same molecular formula, C4H8, and the name of this would be Lut2ene. Still four carbons, but the carbon-carbon double bond is on carbon 2. And whichever side we count from, it will be carbon number 2. We count from left to right, 1, 2, 3, 4. If we were to count from right to left, it would still be carbon 2. 1, 2, 3, 4. So that's one of the structural isomers of butene. And then the other one, I'm going to split this box so we can get the other one. To get the other one, what we would need to do, we would need to take this methyl group, this CH3 group that we have here from the original compound, and we would just replace it, trade places with the hydrogen that's on carbon 2. So let's number 1, 2, 3, 4. So we'll take this methyl group at the end and we will replace it. We'll swap spaces with it and the hydrogen. And the idea here is to get a different arrangement of the compound. It's like playing with Legos. You're taking the Legos and you're trying to make a new structure each time. Well, Legos are good for the mental development of toddlers. So it's a similar process here. Can you imagine Legos helping you with organic chemistry? Right. So if we were to do that, then this is what our compound would look like. So let's draw that compound and we're going to name it. So we'll have still would have our CH2, and then would have our carbon-carbon. Would have our carbon-carbon double bond. But on this carbon number 2, we would now put on the CH3 that we took from the end over this side. So we're swapping space with the hydrogen and the CH3. So we put the CH3 right here. Check. So we would put our CH3 right here. And I'm not condensing it, so I'm writing it, drawing it out so we can all see that it's the same group that we're removing from the original structure. And if we replace our original carbon would have had hydrogen right here, and then this hydrogen that we're moving, let's use green so we can see what's happening. The hydrogen here, we're going to put it now at the end. And that's a different arrangement. So we have the same molecular formula C4H8, but the atoms are arranged differently. So this would have a different name. So it is still 3 carbon atoms long. So the parent name would have to be something with prop in this case, because what we have now is carbon 1, carbon 2, carbon 3. The longest chain has 3 carbons, so it will have to be prop, right? And since it's an alkene, the family is still an alkene, so it will be propene, but other things are present, right? We have a CH3 group on carbon 2 right here, so we'll have to account for that. So the CH3 group is the methyl group and it's on carbon 2. So we're going to give the position of that. So we'll say 2-methyl, and the original name, as we said, the longest chain is 3 carbons. So we'll have to call this propene, prop, and it's from the alkene series. So it would have to be called propene. We say 2-methyl because we're giving the location of the methyl. It's like giving your street address. You're saying 2 Dumpling Avenue or whatever it is. All right. So there's a methyl group on carbon 2. So we say 2-methyl propene. Propene is the longest chain and it's still in the alkene series. Check. Part B. Ethene and propene are typical monomers which are used as starting materials for making polymers. In forming polymers, ethene and propene undergo addition polymerization. Part 1. Define the term polymer. Right? So a polymer is a macromolecule formed from the joining of 50 or more monomer units. Right? Poly means many, mer coming from the word monomer. So it's many monomer units joined together. So a polymer, let's just get this through. So a polymer is a macromolecule formed from the joining of many monomer units, and we need at least 50 of those monomer units. Part 2, define what is meant by addition polymerization. So it's a macromolecule formed from the joining of the same monomer units, and these monomer units are usually alkenes. State one use of each of the following polymers. Polyvinyl chloride, aka PVC, used in the manufacturing, we can just say used to make pipes or electrical conduits. And then another one here, Teflon. I'm sure we've heard this word before, right? Teflon. Well, I've heard a popular DJ call this name Teflon. It's a cool name. This person is meant to be tough, but we'll see that it's not too tough of a name. Teflon is used as the non-stick material that that they use to coat frying pans and pots. So it's used as non-stick material that coats pots and pans. So Teflon isn't so tough after all. The Teflon is actually the brand name. It's really so Teflon is the brand name, but it's actually called polytetrafluoroethylene, and it's made from many of these molecules that I'm drawing here, joined together. So not a tough name, not such a tough name after all. But anyway, let's not get into that. Teflon. Probably a tougher name would be Kevlar, the material they used to make bulletproof vests. But right, I guess it's about what sounds cool and catchy. Part C. There are several different types of polymers. Figure 5 and figure 6 below show the partial structure of polymers. Use the type of polymer shown and the type of polymerization reaction that took place in each case. All right, so we need to state the type of polymer shown here for this first structure. And the tip, or what I use when I am trying to identify the type of polymer, the first thing I do is I look. One, we need to look for the repeating unit. So this is our repeating unit. We need to find our monomer. And well, I won't say obviously, it appears that our monomer unit, we can't say what the monomer unit is. Well, we can. The monomer unit in this case is an amino acid, all right? And we have several amino acids joined together over and over. But what will really tell you the type of polymer is the type of bond that is there, or the type of linkage. So the linkage here, let's circle it. That's our linkage. We see our linkage over and over. All right? Good. And then we see over this side, if we were to connect this end right here to what we have over here, we'll get back one of those linkages. But we're not going to stress that right now. This linkage that we see right here is C double bond O N H. That's called the amide linkage. And whenever we see the amide linkage, then it means that the polymer is polyamide. Right? Could also be called a polypeptide, seeing that amide linkage and the peptide linkage are the same thing. Those are names used to describe them. And then the type of polymerization is condensation polymerization. So it's a condensation polymerization. So whenever we see amide linkage or the ester linkage or the saccharide linkage, like we sound like big words, but this is the ester linkage or the ester bond. Whenever we see that, or whenever we see the saccharide linkage, which is just a bond with O and a bond, whenever we see any of those three linkages, the amide linkage, the ester linkage, or the saccharide linkage, it means we have a condensation polymer here, or condensation polymerization actually took place. All right, figure 6. Let's examine this partial structure. We are seeing a repeating pattern of CH2 and then a CH with a CH3. That's a repeating pattern. All right, that's a repeating pattern. And then what's joining the repeating pattern, which is highlighted in blue, is a carbon-carbon single bond. So it's telling us here that we have an addition we have an addition, or we have addition polymerization taking place. So the type of polymer here would be polyalkene. So this is formed from the joining of many alkene molecules. But when the joining has occurred, we don't end up with a carbon-carbon double bond anymore. So let's take, for example, in this case, we would have had, let's use black. In this case, we would have had CH2 bonded to another C with H, and attached to that is a CH3. So let's put two of them beside each other. Let's look at how we would have arrived at this. So the monomer units would be CH2, carbon-carbon double bond, CH, and here we have a CH3. Because we're looking at the repeating pattern, the repeating units. So this would be, when we put this beside and we join this to another monomer unit, the same type. Those were the only repeating units we saw. So we would have double bond again, CH, CH3. What we do in the presence of the right temperature catalyst, we pretty much cut one of these carbon-carbon double bond. When we cut the carbon-carbon double bond, what will have happening, there will be a space on each carbon node for a bond to be formed. So let's look at what would be the intermediate molecules, what it would look like. So we'd have intermediate, we'd have C with the H, CH2. And because we just cut the carbon-carbon double bond up top, it means that space is available on this carbon for a bond. And then we still have one bond left joining the C to the H, which is also bonded to CH3. And we have a space on this carbon for a bond to form. The same thing happens in the other molecule, the other alkene molecule. So we would have space free up right there, or space freed up right there. We have CH2. Then we would have C bonded to the H, bonded to CH3, and the space for a bond. So I'm going to use some squiggly lines in red to show the bonds and how they will join. So I normally call the bonds a sticky end. So we have a sticky end right here. We have a sticky end right here. We have a sticky end right here as well. And over on this side, we have another sticky end. So in the middle, the sticky ends join. And what we'll end up with is a partial structure similar to what we have here. So if we remove our original illustrations, we can show how we get this. So we could pretty much put on a sticky end right here, right? So this is what we have here. This is that sticky end, CH2. Here we are, CH2 we're reading. So there's the CH2, and then there is the remaining single bond from the double bond that was broken. Then we have carbon with the H and the CH3 right here. And then after that, we have a sticky end. So when these two, let's highlight this. When these two sticky ends join, or these two bonds join, it's like a kind of a knot. That's what we would get right here. So let me draw an arrow. Or just look at the parts in yellow. That's what we have. That's the bond right here. All right, and then we would have CH2, then CH with the CH3, and then we would have another sticky end, and they would tie it on. So that is what repeats over and over. And of course, as we mentioned earlier, the type of polymerization is addition. So look for the repeating unit and you look for the bond. In this case, you're looking for a carbon-carbon single bond. All right? And that's that. With this, you would have gotten 15 marks. So thank you for joining. Please check out the other questions and the other materials that are on the channel. And be sure to subscribe, like, and share the video as well so others can actually learn. Couple later.